In a world where humans live more and more of their daily lives through the medium of computers, battle lines are being drawn between those who study humans and those who study computers. But now, a new breed of researcher is looking for ways to break down those barriers. Social scientists study people, interactions, behaviors, and more through skills like abstract thinking, fuzzy categories, inference, and the judicious application of background knowledge according to context. Of course, social scientists do use computers in their work, but they are often taught data skills, including how to categorize and code responses, evaluate data quality, or detect patterns in and draw inferences from data, without learning to write much, if any, computer code. Meanwhile, computer scientists solve information problems using concrete definitions, absolutes, strict hierarchies and categories, and the clearly defined and scoped variables and rules that computers can interpret. They employ programming scripts, computational methods, and technological tools to collect, manipulate, and analyze data, but they are not always taught how to identify or motivate research projects based on societal impact. But some problems need both kinds of thinking. Human thinking is needed to identify the important problems, consider possible solutions, and connect with relevant information, while computer thinking is needed to work accurately and reproducibly with large volumes of complex data. These mixed problems will only grow more common as resources become digital, interactions, objects, and processes become smart or network connected, or as large volumes of data become available or are updated at faster rates. Neither traditional social science nor computational science is entirely well placed to address these mixed problems. That means that computational social science is not only needed, but is an opportunity to do research with real societal impact that would not be possible without computational methods and tools. For example, computational social scientists can process and analyze large-scale, unstructured data, capture data generated or published in real time, access information on new or previously unmeasurable activities, or combine and work with existing data at unprecedented scales and with more dynamism and complexity than ever before. Computational and empirical social sciences are taking off as social scientists gain computational skills and learn to think like computers, and computer scientists gain social science research skills and learn to think like humans. They will need to switch between thinking like humans and thinking like computers to translate research questions into computational methods and then translate results into effective science communication. Acquiring all of the skills needed to be a computational social scientist presents a challenge. Those drawn to social science by a natural inclination for abstraction, communication, subtlety, and shared societal knowledge might struggle to wrap their heads around computational methods that depend on strict rules, exclusive definitions, and extremely formal or structured processes. At the same time, those drawn to computational research through an intuitive grasp of how information can be logically organized, accessed, and manipulated might become very frustrated by working with the relatively ill-defined, overlapping, context-dependent concepts common to social science, as well as the reliance on assumption and background knowledge needed for interpretation. While difficult to do, the best approach seems to be education and training. Specifically, training aspiring computational social scientists in an 8-step process of computational social scientific method. Number 1. Identify the problem. being as clear and specific as possible about what insight is missing, what pattern needs explaining, and what response is interesting. Also, detail whose problem it is, who else is involved, and what role the researcher will play. Number 2. Explore the problem. Researchers must gather relevant information and perspectives on the problem through surveys, observation, literature reviews, web scraping, API integration, corpora building, app creation, or other appropriate sources of insight on the problem. Researchers must also carefully spell out any sub-problems, processes, relationships, simplifications, or assumptions that are revealed in the information gathering process. Number 3. Concept formalization. Although the relevant concepts may already seem well defined to the people involved, computers are ill-equipped to deal with any ambiguity, context dependency, or natural language terms. All concepts and processes must be made explicit, formal, and computer understandable, as well as human understandable. Number 4. Data collection, software implementation, and verification. Researchers will need to select and implement an appropriate computational method or combination of methods to address the problem. This will be highly dependent on the research specifics. The implementation also needs explicit verification to ensure the conceptualization was correctly translated into software, as computers do exactly what they are told to do, which might not be the same as what they are meant to do. Number 5. Experimentation and data analysis. Run the experiments, create the models, build the simulations, analyze the data, or otherwise implement the processes in the previous step to identify and visualize patterns, reveal and interpret results, or explain outcomes. Number 6. Discussion, policy recommendations, and more. Beyond identifying and explaining the results, the researchers must also draw conclusions about how the work relates to the original problem, how they reveal further problems, or what future research might need to be done. Number 7. Communication, publication, and presentation. All of the previous steps must then be clearly communicated to scientific and lay audiences through multiple means, not only to draw attention to and promote the research, but to effect change in the real-world problems the researcher has set out to address. The communication changes over time, as short-term publication and long-term engagement require different foci. Number 8. Data sharing, documentation, and validation. While verification ensured that the work was done right, validation checks that the right work was done and that it convincingly addresses the problem in a reproducible way. This is not unique to computational social science, but a transparent and well-documented workflow allows other researchers to understand and validate the research. Ideally, this would include providing access to code and data when possible. Despite the apparent linearity of these steps, many of them will require some iteration, with some steps potentially revealing the need for new passes through previous steps. Further, some steps, like documentation, are best seen as applying equally to all of the other steps. Now, the future beckons. It is clear that there are new problems to solve and new questions to ask. Like, at what age is best to teach these different skills? Does the order in which they are learned matter? What is an acceptable minimum level of each skill that allows for effective communication and collaboration on computational social science research projects? What are good ways to balance generalist and specialist skills in collaborative projects? Are there other steps to include in a computational social scientific method, or other skills that need to be taught? The time is ripe for computational social science.